Good day, everyone. I am Laika Marlene Samson and I'm one of the presenters for the Flexural Strength Test in accordance to ASTM C78. First, let us determine the flexural strength. Flexural strength is the measure of the tensile strength of concrete beams or slab. Flexural strength identifies the amount of stress and force unreinforced concrete slab, beam, or other structure can withstand such that it resists any bending failures. Flexural strength is also known as bend strength or modulus rupture or fracture strength. Flexural strength is the ability of composites or materials to resist the bending deflections when energy is applied to the structure. Flexural strength measures the fiber's ability to resist the breaking when pressure is applied. The result helps to ascertain the product's application suitability and longevity as well as the end user safety. Flexural strength, also known as bend strength, refers to the maximum amount of tensile load concrete can bear before falling. Basically, means how far the concrete can bend or stretch before breaking or cracking. Concrete has very little tensile strength because it is not designed to bend. Cracks in concrete roads, sidewalks, and other slabs are largely due to tension or flexing. Many structural components are subject to flexing or bending, such as pavement, beams, and slab. It is important that concrete mixtures have a flexural strength able to resist bending or tensile forces. However, the exact amount of flexural strength required varies on what part of concrete plays in the strength of the structure. The location of the concrete structural element determines the degree of flexural strength importance. For example, concrete used in first floor columns must have much higher flexural strength than concrete used in load-bearing walls. Building codes specify the minimum strength required in different parts of a structure. Calculating the appropriate flexural strength of your concrete is crucial in structural mechanics because it ensures your structure meets building codes and doesn't threaten public safety. Let's move on to the importance of flexural strength. The importance of flexural strength are the following. Calculation of flexural strength is considered crucial in structural mechanics. It helps in designing structural elements like beams, cantilevers, shafts, etc. And it also aids in the study of material and their properties. It also provides a parameter for development of stronger structural materials. Flexural strength helps in judging the quality of structure being used for construction. It is a tool to predict both resistance and durability of the object. The testing objective of flexural strength test are the following. This test aims to determine the flexural strength of concretes, which may express as modulus of rupture. It is also used to determine the ability to withstand the structure in bending condition in accordance to ASTM C78. Scope. The scope of this test is limited only in the road, supported by sub-base cores or unreinforced section, and beams that are subject for application of bending load. The application of load is only limited either for midpoint or third point application. This test also observes the proper procedure on how to conduct with respect to ASTM C78.
Good day everyone, I'm Mark Kennedy Mariano. I will present the apparatus required, safety precaution, and test procedure of flexural strength test. Number 1, universal testing machine. To make concrete rectangular specimen, we need fine and coarse aggregate, Portland cement, tampering rod with spherical tip, concrete rectangular mold, and bitumen material or used oil. And number 3, digital weighing scale, 10 kg capacity sensitive to the extent of 0.1% of total sample. And let's move on to safety precaution. Number 1, before conducting tests, use safety gloves, safety shoes, and apron at the time of test or PPE. Number 2, after test, switch off the machine. Siyempre, para bawas kuryente. Number 3, keep all the exposed metal parts greased para iwas din magkasugat. Number 4, equipment should be cleaned thoroughly before testing and after testing. Number 5, before conducting the test, make sure that no one is around 1 meter radius from testing machine para iwas aksidente. And next is the test procedure. Please watch the video clip closely to know how to conduct the flexural strength test.
Flexural strength test on concrete. The flexural strength concrete is an indirect method for measuring the tensile strength of concrete. The test is made on the beam of size of 150 mm into 150 mm into 700 mm or 100 mm into 100 mm into 500 mm. Then next, flexural strength of concrete is determined by either central point loading or two-point loading. The typical machine used for this test is shown on the screen you see in the video. The bed of the testing machine is be provided with two steel rollers of 38 mm in diameter. Then millimeters in diameter, the rollers is mounted at a distance from center to center is 600 millimeters for 150 millimeters specimen. Then next naman, 400 millimeters specimen into 100 millimeters specimen. The load applied through similar roller mounted at the top. In case of two-point loading, the rollers are spaced at 200 centimeters or 133 centimeters. Center to center. The concrete is prepared as per required grade of concrete and placed on the mold in layers and dumped 25 blows for each layer. After 1 day, the mold is removed and the specimen is placed in the curing tank at a temperature of 27 plus or minus 2 degrees Celsius. It depends upon the requirements. The test specimen is removed from tank and dried at 14 days and 28 days for testing. The specimen is placed on the roller and centered with the longitudinal axis of the specimen. The load is applied at a rate of loading of 400 kilograms per minute for the 150 millimeters and then at a rate of 180 kg per minute for 100 millimeters specimen. Next, finally, note down the load at which cylinder fails by developing cracks. Now measure the distance between the line of fracture and the nearest support. Consider this as if I is greater than 200 millimeters for 150 millimeters and 130 millimeters for 100 millimeters. Then the flexural strength or modulus of rupture FB is calculated by equation FB is equal to L divided by BD square, which is in the video. If L is less than 200 millimeters and greater than 170 millimeters per 150 millimeters and less 100 and less than 133 millimeters and greater than 110 millimeters for 100 millimeters. Then flexural strength or modulus rupture FB is calculated by equation FB is equal to 3PA divided by BD square, where B width of the beam in millimeters and D is a failure point depth in millimeters. And the L is the supported length in millimeters. P is the maximum load applied to the beam in kilograms. N is the distance between the line of the fracture and nearest support in millimeters. Thank you for watching.
So good day again, guys. I am Clyde Vincent Montealto, and after discussing to you about the apparatus required, safety precautions, and test procedures, I will be the one who will be discussing to you about the tabulation of data. So Table 7.0 and 7.1 are examples of data gathered from concrete mixture that is subject for flexural strength test. The equipment used in this test is based on the present apparatus available in CE laboratory that conforms with the ASTM specifications. So here are the calculations that we will use in tabulating data. So to calculate the volume of the fine aggregate, we need VFA is equals to CC, which stands for concrete cement, and it is multiplied by 0.54 cubic meters all over 360. So for the volume of the coarse aggregate, we also have the concrete cement times 0.81 cubic meters over 360. So for the water to cement ratio, we will just need to divide the water content over cement content. So for calculating the required flexural strength, we need required flexural strength is equal to dimension of the specimen and correlation factor multiplied by correlation factor. So to determine if the flexural strength of the structure is passed or failed, so if the acquired flexural strength is greater than the required flexural strength, it means that the flexural strength of the structure is passed. And otherwise, if it is less than the required flexural strength, then the flexural strength of the structure is failed. Okay, so for table 7.0, wherein the examples of details of concrete mix design used in flexural strength test, we have 3 samples here. And for the class of concrete, we have selected a class A concrete mixture. So for the volume of fine aggregate, we know that the formula for calculating the volume of fine aggregate is equal to cement content multiplied by 0.54 cubic meters all over 360. So by using the data given here on the table, we can calculate the volume of fine aggregate, which is for sample number 1, we have 50 times 0. Okay, so let me show it. So we have 50 as the cement content multiplied by 0.54 cubic meters all over 360. We will get 0.0075 cubic meters. So for sample number 2, using the same formula, 50 times 0.54 cubic meters all over 360, we have 0.008 cubic meters. And for sample number 3, we will get 0.009 cubic meters. So for the volume of our coarse aggregate, we know the formula is same as the cement content multiplied by 0.81 cubic meters all over 360. So by using that formula, we can get 50 times 0.81 cubic meters all over 360. We will get the volume of the coarse aggregate for sample number 1, which is 0.0117 cubic meters. For sample number 2, we will get 0.0124 cubic meters. And for sample number 3, we will get 0.01 140 cubic meters. So moving on now for the table 7.1, or the examples of flexural strength test result. So we have here our same three samples with their dimensions, the numbers of their days cured, and correlation factors, as well as their acquired flexural strength. So how do we know if an flexural strength test will pass, or if the material used in the test will pass? So we shown it on the calculations page, wherein we know that if the acquired flexural strength of a material is greater than its required flexural strength, it will pass the test. So we will moving on now for our table 7.2, wherein we can see the required flexural strength for our materials. So in this table, this will serve as the basis for the remarks of our flexural strength test. So as you can see here, this is the required flexural strength for a material in megapascals, and this is the required flexural strength for a material on PSI, and this is for kilonewton. So as you can if you can remember, on the last table we shown that the days cured of our sample number 1 is 7 days, and it has a acquired flexural strength test of 4.25 megapascal, which we can see here it is greater than 3.10 megapascals, which means that the material used for our sample number 1 has passed the flexural strength test. So for our sample number 2, we can remember that it has been cured for 10 days, and it has acquired flexural strength test of 3.10 megapascal. So if we can see here that the required flexural strength test in megapascals of that sample is 3.48 megapascal. So we know that sample number 2 has failed the flexural strength test. So for our last sample, we know that it has been cured for 14 days, and it has an acquired flexural strength of 6.9 megapascal. So we can see here that the required flexural strength of that sample when it was cured for 14 days is 3.79 megapascal. So we can identify that the sample number 3, or our last sample, has passed the flexural strength test. So that's all for our tabulation of data, and I hope you learned something, and thank you for listening. Thanks. Bye.